Hi, I'm Chang from the University of Texas at Austin, and I will be presenting our paper on defining fairness in human-robot teams. Fairness has been shown to be the foundation of trust and team effectiveness. Understanding fairness is challenging because it is preference-based and context-dependent. In HRI, there is still a research gap in our understanding of how fairness is defined in human-robot teams. One method uses a multi-arm banding algorithm and define fairness as a constraint on the minimum rate that each human teammate is selected to play. Different from this work, we propose to define fairness in terms of workload, capabilities, and task type by studying the effects of a robot's behavior that is characterized by fluency and effort. Researchers have addressed the concepts of fluency and effort separately in HRI. Different from prior work, we investigate the impact of both fluency and effort on the human teammate's perception of fairness. To seek this understanding, we conducted a user study. We focused on the team scenario where the robots and human skills complement each other. The task involves the robot and participant collaborating to sort 20 items from a table into 2 bins. An external monitor displays a GUI showing the current state of the table. Each item has an associated math problem that needs to be solved first to get a code that reveals a bin for the item. We manipulated 2 independent variables, fluency and effort. Fluency describes if the robot minimizes the idle time between the human's action and the robot's action. Effort describes if the robot performs manipulation, i.e. tasks that it is worse at, as quickly as it can. This resulted in 4 human-robot teaming algorithms, which I'll describe next. I'm going to go through the timeline of one possible interaction during the fluency present and effort absent condition. Let's say this person prefers to alternate between math and pickup. She starts with math. As soon as she completes it, the robot shows fluency present by immediately taking an action, which is math. Next, the human does a pickup. As soon as the human finishes, the robot immediately does another math. This repeats, and when all the math problems are solved, the robot does pickup in order to exhibit the fluency present behavior. Next is fluency present, effort present. Assuming the person is the same as before, since effort is present, the robot also does pickups as fast as possible. For fluency absent and effort absent, the robot solves the math problem every 2 seconds and does not perform any pickup. Now for fluency absent, effort present, the robot solves the math problem every 2 seconds, and at the same time, the robot performs pickups as fast as possible. We found that when the robot was effortful, this resulted in a significant 27% increase in participants' fairness ratings. In addition, the post-study questionnaire results point to 2 types of allocation fairness, capabilities and task type. We categorize participants' comments, and the majority define fairness based on task type. One of our objective measures of fairness is the ratio of total tasks. It is a ratio of the difference between the number of tasks, math and pickup, that are completed by the robot and human to the total number of tasks. The ratio of total tasks is in the range -1 to 1. A ratio value of 0 means the work is balanced. 1 means that the robot completed all the work, and -1 means that the participant completed all the work. Our analysis shows a significant interaction. Post-hoc comparisons indicated that when the robot displayed effort present and fluency present, which is working on math and pickups as fast as it can, this enabled the robot to be significantly fairer than the other 3 conditions. To further understand the task breakdown, we analyze the ratio of math tasks and ratio of pickup tasks. The ratio of math tasks is the ratio of the difference between the number of math tasks completed by the robot and human to the total number of math tasks. The ratio of pickup tasks is the ratio of the difference between the number of pickup tasks completed by the teammates to the total number of pickup tasks. These metrics are also in the range -1 to 1. For the ratio of math tasks, in general, the robot completed more tasks than the participants. Both main effects were significant. Effort present was fairer than effort absent. That is, when the robot was effortful, this enabled participants to complete more math. Fluency present was fairer than fluency absent. This means that when the robot was fluent, this helped participants complete more math. For the ratio of pickup tasks, the participants pick up more items than the robot in general. The interaction was significant. Post-hoc comparisons showed that effort present and fluency present was fairer than the other conditions. That is, the robot completed the most pickups in this condition. Based on our results, we provide formal definitions of fairness for a single robot, single human team. We are interested in answering the questions, which algorithm is the fairest? If an algorithm is unfair, who is it unfair towards? We propose 3 notions of fairness. Our first fairness metric is equality of workload. It is the ratio of the difference between the number of subtasks completed by the robot and human to the total number of subtasks. This metric is in the range -1 to 1. Equality of capability is the difference between 2 terms. The first term is the ratio of the number of subtasks completed by the robot, that is its strength, to the total number of possible robot strength subtasks. The second term is the ratio of the number of subtasks completed by the human, that is his strength, to the total number of possible human strength subtasks. Equality of task type is the linear combination of the equality of workload metric across all task types. For a specific task type, the equality of workload is the ratio of the difference between the number of subtasks that are of task type I that are completed by the robot and human to the total number of possible subtasks that are of task type I. In summary, a robot's effortful behavior increased participants' perception of fairness. Also, participants consider team members, skill levels, and task type in their assessment of fairness. To that end, we propose 3 notions of fairness for effective human-robot teamwork. Lastly, thank you to my co-authors and the organizations that make this work possible.